Hi everyone, welcome to the third session of PEPM. I'm the chair of this session. We have two talks in this session. The first talk is going to be done by Fred and Denis. And partial evaluation for MATLAB. How cool is that? So, Fred?
All right. Well, good afternoon, everyone. So as Sukyung, all right, announced, Dennis and I will be presenting. We both are part of the MATLAB Coder team, and what we'll be talking about is the product that we built. So when we started this project, which was more than a decade ago at this point, the question was, can we use a high-level language like MATLAB for embedded systems implementation? So let's start by examining that question. MATLAB is loved by engineers and scientists for doing prototyping. Right? It's very, very flexible, and it's just easy to use. It's dynamically typed, it's got nice math syntax, it's got a huge numerical library, and it's got a very forgiving semantics. So this is all conducive to that exploration of trying to discover a new algorithm. It's got great visualization capabilities. On the other hand, most embedded systems are implemented in C code, more recently in C++, and what I'd label their embeddable C or C++ code, which just means that you're trying to get rid of runtime errors. You want everything to be static. You would like to detect errors at compile time, not at runtime. You want the code to be easy to understand so that you can be reviewed, so that you can get some safety assurance through some process that's mandated by some certification body. You need to meet, and you have engineering requirements. You have timing requirements and memory requirements that need to be met on some particular piece of hardware. And typically, you don't have much of a runtime other than the C runtime. So you're not going to have a complex garbage collection machinery or anything like that in an embedded system. And in fact, many of our customers have organizations that are structured exactly like this. They have a team of researchers that loves MATLAB, and they use MATLAB every day to come up with new ideas. And when they've got an algorithm working, they hand it to the systems team and say, here's my MATLAB, this is my spec, go implement it in C code for me. Right? And so then that team takes the MATLAB code and implements it in C code. And obviously that's error prone and laborious. So the challenge for us is, can we make this MATLAB code that they've developed in the first place for prototyping, can we make it possible for them to reuse that MATLAB code in production? So can we convert that MATLAB automatically to that embeddable C code that they want to use? So the first thing you'll notice if you look at MATLAB, actually I should say before, if you aren't familiar with MATLAB, you can think of any other dynamically typed scripting language, and for the purpose of this talk, it won't make any difference, okay? There's nothing particular about MATLAB semantics, although there are a million details to get it right, but from a programming language perspective, I think we can ignore those. So in MATLAB, you can write A times B, and you have no idea what that does, right? That could be a scalar multiply, it could be a matrix multiply, it could have sparse data, it could be complex, it could be fixed point math, it could be overloaded with some custom user data type. So the first observation when you look at this problem is that we're going to need someone to tell us what type they want to use that code at. So like when I call this code that I've implemented in MATLAB, but I'm somehow getting on my embedded system, what type of input am I going to give it? So we're going to need that information from our user. So that's the first observation. The second is that although we would love to support all of MATLAB, that's really not our key goal. We just want to support a very significant subset of MATLAB. And so that, our customers really want to generate embeddable C code. That's the main goal. And if we have to sacrifice some things in MATLAB, that's okay. We just want to make sure that it's still much cheaper than re-implementing the whole thing in C. So MATLAB has some really dark corners that very few people use. We're not going to support that. For example, in MATLAB, you could CD to a different directory and change the semantics of your program because you'll find different files on the path. Like, we don't support that, right? That's not a thing that you want to do in an embedded system. It's also not a good idea in general, but put that aside. So the other decision that we made early on is to, instead of starting from a system that was very powerful, supported a lot of MATLAB, and then trying to figure out how to get it into an embedded system, we figured let's start with a smaller subset of MATLAB that meets our requirements and then try to grow from there. So the first decision we made is no boxing of values. So what that means is that in MATLAB, at runtime, you have the data that you care about. Say it's a double matrix, you also have metadata that says what's the size and what's the type of that data. So you have metadata and the runtime data that you care about, and we don't want that metadata to show up in the generated code. We want it to all be gone. We're not going to have a runtime library because we want to be super portable and support a lot of different hardware. So we're not going to do that. We early on decided that C was the right language for us because it's kind of portable assembler, lets us target many different pieces of hardware. We've gotten pretty sophisticated with this and gone beyond C at this point, but still that's where we started. We know that for many engineering applications, about 30% of our customers can't use dynamic memory allocation in their applications. So we decided to make that an opt-in. We're not going to talk much about those capabilities today, but that is there. And then to do type inference, we decided to use partial evaluation, in particular online partial evaluation, which might surprise you. You might think that we should just do sort of natural type inference. The problem with type inference is it looks at the whole program, and there may be paths that are not executed in any particular instantiation of that code. And so you really don't, in an embedded system, you don't want all that code that you don't need, but you also don't want to type check parts of the code that aren't running because it might fail to type check and it might pollute your types with all kinds of extraneous data that isn't actually relevant to the application at hand. Okay. And I'll show you examples, we'll show the product in a little bit. The reason it's online with partial evaluation instead of offline is that in MATLAB, function calls are dispatch is type dependent. So there's a phase ordering problem. Like you need to know the types before you know what you're calling. So you can't do a binding time analysis because you don't have the whole program to figure out what's going on. Okay, so you need to do this online. And then if you think about this problem for a while, you'll realize that, well, how are we going to do this for that? Because MATLAB is way more than the language. It's also the toolbox, right? There are all of these functions. So MATLAB speak for a library of functions as a toolbox. So there are many, many functions in MATLAB that people expect to be able to use. And so how are we going to make those work? And the reality is we've had to re-implement all of the functions in MATLAB. At this point, we're running about 3,000 in a subset of MATLAB that supports code generation and this partial evaluation we're about to describe. So it's a very laborious thing, but we have to do that because much of MATLAB is implemented as C and C++ code that's not amenable to our tool. Like our tool can't access it and analyze it. It's also not written with the assumptions that we require for embedded. Okay. So in this talk, we are going to talk about the key type inference algorithm or the type inference engine. And what I wanted to do was show you some examples. But normally we give this talk, we're teaching people how to use MATLAB Coder, and there's a whole bunch of stuff. There's UI, there's an app, there's all kinds of workflows. We're not going to go into any of those today just for lack of time. And it's not the interest in this audience. So we're not trying to teach you how to use the tool, but we do want to give you a taste of what it looks like. So let's start with a simple example. This is one of our Shippig demos that I modified slightly. This is a Kalman filtering algorithm. And sorry, this is a Windows machine. Scrolling goes the other way. So let me try to run the first section here. So what we're doing, okay, is we've stored some data for a bouncing ball. Okay, this is just data we loaded. You'll notice that the ball jumps suddenly discontinuously to another part of the screen. And the algorithm we have is a Kalman filter algorithm. We have this function called object track. Okay, and the job of this function, if we just run it now, is to predict where the blue ball is going. So the green is the prediction, and the blue X's are where the ball came from the data set we just loaded. And the job of the algorithm is to look at the past data, predict the future position. And you can imagine this would be useful in an engineering application. So this really has nothing to do with code generation. It's just the type of thing that people like to do in MATLAB. And we can look at this Kalman filter algorithm, which is the heart that's doing that prediction in the green. And this will just give you a flavor of what MATLAB looks like in case you haven't seen it. So you have sort of matrices, and I hope a pretty natural matrix syntax. We have, in this case, we have persistent data. That's sort of memory. We're remembering what happened so we can use the past to predict the future. We have some matrix arithmetic here, where we're just doing a transpose. We're multiplying some matrices. And this backslash here is sort of the prototypical MATLAB operation, which is solving a system of equations. So this is what the code looks like. If we go back to our example, I can show you how you would generate code for this example. So here in the dark gray are the commands. So first we're going to create a code generation configuration. Has many options. I've just set up one to make the generated code easier to look at. We have a value that we're going to use as an example. So MATLAB Coder has this idea of you give us an example value, we'll tell you what type it has, and then so you don't have to construct a type. Doesn't always work perfectly. You have the option of constructing a type explicitly if you want, but then this is the command that you run. It's the codegen command that actually does the code generation, where you pass it the configuration. We're asking for a report. We're saying not to compile the C code because we don't care about that right now. And the Kalman filter is the name of that function I just showed you, and -args is telling you the types of the input arguments. And this is the information we need from users. Tell us the types of the input arguments you want in the generated code, and we'll propagate it from there throughout the rest of the code. So we asked for a report, and we got it. So for the rest of this demo, I'm going to be using the report quite a lot. So let me open that now. Yeah, so this is what the report looks like. So on the main screen, you see the MATLAB code that we started with, but there's a big difference that if I hover over this MATLAB code, you can see the types of all the variables and their sizes. Okay, so this is from the input specification. We told the compiler we wanted a 2x1 double input, but you can do this over any expression in this code. This is what our algorithm has figured out. By analyzing the code, we found the types of everything in here, and you can look and see the size and type of every expression, every variable. Another feature we provide is to trace from the MATLAB to the generated C code. Let me make this a little bigger. Okay, so you can hover over an expression like this, say where did that go, and there you see a call to ML divide on the right. That's the C code, and it says that that slash operator went to that call. Okay. Right now I don't want to look at the code trace because I think it's too much information, but let's look at just the Kalman filter.c, and here's what we mean by unboxed values. We see that everything is just native C types. We don't have any metadata wrapping around these. And this code hopefully looks relatively ordinary C code that does the task. Okay. So that's your first taste of MATLAB Coder in action. There's a lot more here, but let's move on to the next. So I've pre-generated those reports for a bunch of examples. These are much simpler examples designed to illustrate specific points. So the first one is I wanted to show you how MATLAB, because it doesn't have a distinction between types and values, how values and types really interact. So what we see in most of our customer code is that it's pretty straightforward, but when you're looking at our library code, the functions, they're very, very polymorphic. They support all kinds of inputs. And the way those functions have to be implemented, they have to introspect the inputs and make decisions about what code to generate. And so this is kind of the pattern that you typically see. So this class function in MATLAB gives you a string that's the name of the class of the object in question. So in this case, I happen to know I think it's a double matrix. I've been trying to keep the type simple here. Yes, it's a 3x3 double matrix. So class of A is literally returning the string double, right? And then we can use that string to construct a new value that has the same class, right? So this is how you can see that it went from a type, it flowed into a value, and then we used it, in this case, in a simple way to compute a new type. Okay. The size function similarly gets a size as a vector of doubles from a matrix. And here we're doing a little computation and constructing a new output C using the size of the two inputs. And you'll notice that in the tooltip that we computed the size of C. So we've constant folded that. We know it's a 5x5. Right? It's not very interesting what this function does. It just takes A and B and puts them on the diagonal. This is a trivial example, but this is very typical, this kind of pattern where things flow into values, you do a bunch of analysis and computation, you make some decisions, and then you construct your output result. Next, I wanted to show you what some of MATLAB's functions look like. These are examples of calling the sum function. Okay, so sum, you would think, how complicated could it be? It just adds up the elements of a matrix. Well, no. In MATLAB, things sum columns. So sum of just A adds up the columns of A. So I made I think here, it's a 3x4. So this gives you a 1x4 output. You can say, no, I didn't want to sum the columns, I want to sum the rows. So you can pass it 2, and then you can say, the sum has initial flags. You can say, I don't want you to consider nans. Typically, so for those who don't know, floating point has a notion of a nan value, which is not a number, and usually pollutes your output. So you have one nan, everything becomes nan. But this says, skip the nans for me. I'm not interested in them. Sum A of all says sum all the elements to produce a scalar, right? So regardless of how many dimensions A has, sum everything up and make it a scalar. And then, of course, sum also works with N32 and complex and other things and has other options. So now let's look at what we produced in terms of the generated code. So we can go and look at the what we generated in this case. And what you'll see is that we generated, I think, 4 different versions of sum. So here's this is, I think, the version that skips the nans. Okay. And then here we have, this is the version that produces a scalar. This is the integer version of sum. And this is the one that sums the rows instead of the columns. So we have produced multiple versions of sum out of that same code. Okay. And just for kicks, I thought I could show you how we implemented this. So the sum for code generation is not the same sum that MATLAB uses in its normal execution. So this is the body of the sum that does code generation, has a bunch of coder-specific intrinsics. At the bottom, you'll see it calls sumProd, and that's because whoever developed this factored the code. So there's one function that does the sum and product functions. And so this is actually the code. And if you looked at this code, what you would see is that you only actually start doing a sum around line 40 or something. Most of this code is just parsing those input arguments. Because MATLAB is really flexible. You can pass the flags in any order. The flags, some of them are optional. Most of them, they're all optional in this case. So there's partial matching. You don't have to give the right, you can misspell things. Like if there's too short, it'll guess which one you meant. There's a whole bunch of logic that's happening here. So this.
So does that mean when before you said, notice we did constant following, we got a plan?
Yeah.
So that's to get there. So that's to analyze this code.
Yep. So yeah, so we're partial evaluating all this code that does argument checking. Okay. No, that was the wrong thing. I didn't want to close that sheet. Okay. All right, this will take a second. I have 2 more examples to show. I was ready to do that. Sure.
How many people are online? There was 2 online attendees. Okay. 3, sorry. 3. Oh. I have already some questions from them before. If they have a question, yeah.
So the next example I wanted to show you was errors. Errors are actually surprisingly subtle because we are partial evaluating and we are pulling things into the context. We may, in theory, be partially evaluating code in a context that never executes at runtime. If there's some control flow that we don't understand, we don't know it's always true, we may partially evaluate there, and then it would be wrong in a way to say that it's a compile time error. But what we've seen in practice is that for this embedded use case, it's much better to tell people compile time about errors than having them discovered at runtime. So even though in theory, it might be the case that you're not actually calling it at runtime, if this is all in dead code, we do aggressively promote runtime errors into compile time errors. So in particular, I constructed a 3x4 matrix A, and I'm taking its inverse, and inverse requires a square matrix. So we now get this error message if you run CodeGen that says the matrix must be squared. Okay. You can also write a user assertion, which basically says the same thing, so that is square. And here we're a little bit more subtle. MATLAB Coder will tell you this assertion is always false. It's a compile time error. But we have an internal command, coder.ignore const, that you can say, if you really want to turn this into runtime for some reason, I don't know why you'd want to, but if you want to, you can. Okay. So I think, but in general, we promote most runtime errors to compile time errors. And that hasn't, I don't recall that ever being a problem for a customer. Okay. And then the final example is just our latest feature in the upcoming release. So I'm running the pre-release now, which if you have an account is available. And what this allows us to do is to do loop scheduling using sort of partial evaluation. So we let the user tell us what loop schedule they want and apply it to a loop. So here they're saying, construct a loop control, and then depending on the layout of my matrices, again, this is a code generation feature, you can have row major, column major matrices. I want you to, for example, interchange the row and the P loops and parallelize the row loop. And if we look at the generated code, you can see that that indeed happened. Maybe I'll make this a little bigger so it's easier to see. So here's the loop. So we parallelize the row loop, and we move the P loop to the bottom, but the P loop got unrolled, so there is no P loop left. Okay. So this is a way that the user can achieve effects similar to what Halide can do, but very locally on a specific loop nest. And this was extracted from one of our image processing algorithms. Okay.
And the reason you can do this is because you use dynamic. This thing was
So we partially evaluated that we constant folded the if, it was gone, because it was just dependent on static properties. And in fact, you can query hardware properties and say, like, if I'm on this processor and my data is over this size, then schedule the loop this way, otherwise schedule it this other way. So it's actually very powerful in terms of what you could in theory do. It's all static data. Yep. Okay. So that's it for my demos. Let me get back to the talk. So I've shown you these examples. So first point that I tried to make, I don't know how successfully, is that we need types for the entry points to drive, to kickstart the analysis, because we need to know what context the code will be running in. It's hard to convert MATLAB to static code because types and values kind of flow throughout the code. Functions in MATLAB are highly polymorphic with these complicated signatures. We have a problem that which values influence types is not obvious. I skipped one of the demos, but it's generally true that you need to do this online because you don't know in advance what's going to be needed. And we promote errors from runtime to compile time. And finally, I showed how users can use directives and partial evaluation to optimize the code in my last example. So now I'm going to hand it off to Denis, and he's going to tell us about the actual algorithm.
Am I audible? Yep. All right. All right. Hello, everyone. So I am going to talk about the type inference algorithm itself. And moving forward, what we mean by type inference here, because it's a term we kind of coined on our own, it may not be a standard one, is a thing that takes an untyped IR and the entry point specification, the types for the parameters to the main function, and produces an IR which is statically typed and generally and naturally mappable to a language like C or C++. Since we are talking about type inference, we need to talk about the type system a little bit. And here it's a mix and match of the MATLAB's type system and the things we added to that. Specifically, there's the task of doing static type analysis, static type inference. I am not going to go into the details in all the singleton types and how we deal with reference objects. It suffices to say that for the purposes of partial evaluation, what's important for us is that the type system uses concrete primitive types. So we have integers, we have doubles, we have strings, and we don't do union types. It's either this or that. And we compensate for that simplicity by adding the complexity on the array shapes. Because MATLAB is a tensor language, so the type system has things such as an array of 3 elements versus array of unknown number of elements, but up to 3, no more than that, versus an array of unknown number of elements that can change from run to run, what we call variable sized. So those two things suffice for our purposes today. But if we have time, we can talk about heterogeneous arrays and dictionaries and all these interesting things that make the picture much more sophisticated. So we start with a program being parsed into an ASTs. We convert them to control flow graph, essentially statements containing expression trees. And we're given by the user the specification of the entry point. In this contrived example, silly example, the first input is an array of doubles, second input is an integer, and the user told us a value 3, meaning that they want to specialize this algorithm for that particular value. Right? So the first type inference for one statement, it's natural because we have this invariant that the types of all the variables are known to the engine before they are being used. And given that, if you have a statement and you know the types of all the variables that occur in that statement, like bottom-up traversal gives you the types of everything. There are all kinds of details because MATLAB has a crazy number of built-in operations and so on. Things like array reshapes, array concatenation, transposition, and so on. But conceptually, bubble the information bottom-up, you get to the top of the statement, and then very simple rule. If the variable on the left-hand side doesn't have a type yet, all right, here we go. Its type is now computed. If it has a type, well, we're going to type check it and error out if they don't match. I'm making it very simple. In reality, there is more to that. The type of the variable can be a union of types of multiple assignments. We have, what a good example, structs, dictionaries, and so on. But again, for the purpose of spatial evaluation, type is assigned through very simple typing rule. You see a variable, assign to it, and then use it. Right. And then what happens is essentially the type inference engine takes a brush and paints the AST one statement at a time from the gray color to the green color, where a gray means this is untyped IR. It may not be semantically correct. It may be ambiguous. There are dragons there. And the green means I've seen those statements, I've elaborated them. You can do program analysis on those statements. Right? So we partition the function into two parts and move that down, one statement at a time. Right? So type mismatch, in this primitive example, if this type mismatch was observed by the engine, it would go back to the user and tell them, your program is not statically typable, please go and change something. Give me more data, edit your code, and what's not. Right? So as Fred said, no boxing, no union types, no dynamicity here. The example is specifically designed to make this unnecessary because what would happen is that we do constant folding. So when that if statement is elaborated at that time, the heuristic would say, well, I really want to know the constant value of this condition. Can you figure it out? And build a useDef graph. For that function, notice that all the definitions of D, they are in the green part. We have seen them. The definitions that flow to that computation are also in the green part. Build the value dependency graph and feed it to the interpreter that runs and produces an answer. Right? It's a simple example, but it kind of shows how we deal with all those overloads and compile time things, such as deciding what arguments a function sum has. Right? So the control flow is pruned, and the type inference engine actually doesn't see the second assignment to E. Right? So there is no type conflict from its standpoint, because the constant folding kind of prevented it from happening. It was the first interesting nugget. So we do constant folding and pruning, control flow pruning during type inference to aid it. Second interesting nugget, what do you do with function calls? And we do specialization on concrete types. So here we get to this line with a call to foo. First thing, as Fred said, that the function dispatch rules are type dependent, so they cannot be done ahead of time. Now, since we have the types for the variables, we know which foo to parse. We parse it, and then we say, well, can we specialize it against those concrete types? Well, create a new clone of the function and recursively run the same type inference algorithm on that function. Right? So the inference of main stops. We create a new inference engine and go to static, like no dynamism whatsoever. Same thing is going to happen is that it will try to do the type checking, and it will fail with type mismatch. Now the interesting nugget of the algorithm is that we don't fail here. We just backtrack. What it means, we scrap the inference of who, go back to the call site and say, is there more information we can use? And since it's possible to specialize on the values, let's run the constant folder to see if the inputs to the function can be constant folded. Yes, they can be constant folded. Let's try to specialize again, this time in what we call stronger context, binary on values. That succeeds, and the type inference proceeds. In this slide, I make it look like it's very simple in a sense that we either specialize on types or on values. In reality, that's heuristic driven, and there are several strands of optimization in the sense that it's more beneficial to specialize on an integer value. then it's beneficial to specialize on a huge array of double precision numbers. Beneficial, I mean that the compiler, when it does it, it doesn't know if specialization is going to help to avoid the type mismatch error or not. It makes a guess. It says, if I got an error, maybe specialization would help. I might do unnecessary work by doing that specialization. That's the case. That's why it gradually tries more and more specialization until it either succeeds or fails, and then the error goes to the user. Right? So that's the second interesting nugget. The third nugget I put in over the lunchtime, because I felt that the presentation is too trivial for this audience, is that specialization can be made to work to help with type check and examples that are different than calls and if statements. In this example, what we have a heterogeneous array, a cell array in MATLAB speak, which is a tuple. Elements of the tuple have different types, and if I write a for loop that iterates over the tuple, that by itself is not statically typable. Right? I don't know which element you are referring to, therefore I don't know if it's an integer or a string. Right? What the algorithm is going to do, it will try to constant fold the bounds for the for loop, which are natural 1 and 3 here, and then it would, heuristic driven, completely unroll that for loop into a series of straight like for loop bodies interspersed with assignments to the index variable, and feed that to the inference engine that in this contrived example that specializes just fine, and type inference can proceed. That's a very dangerous thing, right? You can blow out the code a lot. But this argument parsing in compiled and polymorphic functions, that's exactly what helps there. That's essentially all the nuggets that I want to show. So the summary is that we use concrete types, very simple typing rules. Right? We use very aggressive constant folding and control flow pruning in type inference engine. And these things bounce to each other. So type inference delivers information to the constant folder that helps type inference move forward. Right? Function specialization on types values. Specialization on values is kind of reluctantly. Like, let's not do that unless we get an error. Then let's try to do the minimum of it. No good dependency checking. Essentially, this is like a trial and error approach and backtracking. And I think the empirical evidence we got is that for the kinds of applications that people use MATLAB for, like heavy number crunching with some amount of scaffolding code around it, this works. This works better than we would have expected. So we say that you write programs in dynamically typed language. Well, you really write in statically typed program if you look at them at a proper angle. Yeah.
MATLAB supports some kind of overloading.
Yes. Yes.
So it's kind of, I feel that it flows in and out of your story with this kind of tracking and stuff. Am I right?
So, not sure I get the question right. I can easily write an example that would not be typable through this simple algorithm, right? I can like write arbitrary polymorphic code. Our point is that people don't tend, the engineers don't tend to do that. Almost never. Not really. What they want to do, they want to write a numeric algorithm. Even for them, if they need polymorphism, they put a bunch of if statements into the code. They don't naturally think about function overloads or abstract classes of interfaces. For them, it's easier to pass a parameter, which is value 1 means transpose, value 2 means filter, and so on. And that kind of polymorphism is resolvable through partial evaluation to a very large degree, right? So again, I made it sound if it works. In practice, it almost works. We spend a lot of time dealing with the cases where it doesn't. So where it doesn't work yet, and what we want to do with it. So the big story here is that this algorithm is very strict. It's stricter than it needs to be. If a type checks a program, great, that program is embeddable, but it might not work. It might give you an error. So what we are trying to do all the time is to make the algorithm more precise, like make the type inference more rich, right? So some things that on the plate for us right now is, first, we need union types. Not for combinations like it's an integer or a string. That doesn't seem to happen in practice. But for the combination where this object is either a class tracking pedestrians or an object that is tracking road signs in autonomous driving. So some kind of like polymorphism in a sense where you do it in C++, where you need to extract a base class, create virtual methods and all that. So kind of translate duck typing into class hierarchies, right? Second thing we are doing right now is trying to make the type inference to be more potent by reducing the unit of typing. Right now, unit of typing is a variable. Each variable has one concrete type, pure function specialization. Arguably, that's not too granular. If we convert the program to static single assignment prior to type inference, then the unit of typing will be a variable version. And then you can have more precise types, saying in this branch of the if, this is a vector. On the other branch of the if, this is a scalar. Okay, at phi function, they merge and produce some other more general type. So again, SSA typically is used in the compiler optimizations. We're trying to use it essentially when program is being elaborated. Right? Type narrowing kind of makes sense. MATLAB code is interspersed with examples where you say, if some property of the variable is true, do this. Well, we can narrow the type of the variable based on that guard, right? What TypeScript does, right? This is what we want to do, and things we don't know yet how to handle in a good way is these other challenges below. Obviously, function specialization, driven by heuristics, sometimes produces ginormous amount of functions, sometimes unnecessarily. If I write a function that returns true, if all elements of the array are positive, that function doesn't need to be specialized 10 times for arrays of different sizes. And yet, depending on how I write that algorithm, the heuristic might decide to kick in and do this over-specialization easily. Right? And then we are now thinking, shall we try to reconstruct steaks from burgers? Or do we control the specialization better? Tune our heuristics. It sits on the table. Type mismatch errors. It's not that type mismatch errors are difficult for us or for our users. It's our users are not software engineers. They are engineers in different domains. For them, the whole notion for type is not familiar. And when you give them type errors, that's why Fred showed that report, where if you give them an error, we at least should show them everything we've computed so far about this program that might help you to understand where this type error comes from. Right? So that's an open area for research. And then this algorithm that we presented, where we go depth first on a call graph, specializing functions as we go, it's not naturally parallelizable. It's not naturally incremental in its nature. So for big examples, this thing is slow and you need to do something about it. Right? I mean, there are solutions. It's just they're not natural. This algorithm doesn't scale sort of like MapReduce. Right? More nuggets here is that when we started this project, the intent was, okay, we built static type inference engine, and we are done, right? As it turned out, if you want to go to embedded systems, apparently you need to do more than just static type inference. There are other sources of dynamism in the program that people who work on embedded systems find undesirable. So in no particular order, dynamic memory allocation, they don't like it. Therefore, we have this upper bounds analysis to estimate statically how big every array is going to be and put it on the stack, instead of heap allocated vectors, right? Same for the dynamically allocated for objects in the heap, garbage collected objects. If you can build some sophisticated escape analysis, you can estimate the lifetimes, put them on the stack on a Coder function. Then you don't need garbage collection, right? Right. Then runtime undefined values. In MATLAB, it's very handy language. If you forgot to assign a value to the variable and you read that value, it's an empty value. Very, very, very handy for research, really bad in production if you suddenly happen to have an empty value in some control flow. So we built a static analysis that proves that there is no empty values, flow-sensitive forward data flow. And the final thing here is that once you have static typing for an engineering program, you can mess up with the numerics. Right? So you can say, well, okay, I have the program, can I replace floating point with fixed point and then run it on a machine without an FPU? That's a whole new field. I'm not claiming any credit here, but static type inference is what makes it possible to start thinking about translations like that.
I want to make an editorial comment on the third point. If you could get this death before use analysis to work, it would also benefit your static single assignment algorithm, because if you guarantee that death before use is just always true, then and you convert to SSA, now you will get what's usually known as strict, right? Which usually works much better for all kinds of
Yes, phase ordering problem. We convert to SSA before type inference, which is a semantic engine, and only after that we can run def before use, because you need the program to be semantically correct. So our def before use actually doesn't run on SSA at the moment. It runs on a normal IR. Conversion to SSA would be beneficial, but everything depends on everything. Yes, exactly. So I think the nugget of what we are doing is that not only everything depends on everything, but you start with untyped, semantically incorrect program. And in the middle of figuring out what that program does, you need all that everything. All right, Fred, back to you.
hopefully that works. Okay. So yeah, so we're just wrapping up now, just a few more points. So once you've gone through all this trouble to convert MATLAB to a statically typed IR, there's a lot you can do. Right? So this is sort of a diagram of our compiler. Today we've talked about targeting CPU with C code. We also have the ability to target GPUs with a product called GPU Coder. We generate CUDA code. We also have the ability to target VHDL and Verilog, so we can run code on an FPGA or an ASIC. We can target PLCs, which are basically factory automation systems, sort of CPUs in a box, but they have their own coding standards, so we can target that. And beyond just generating code, once you understand what the MATLAB code is doing, it's really useful to do formal verification. So we have products like Simulink Design Verifier that let you, for example, use model checking to find tests that give you full coverage for your code, or to verify that some assertion in your code is never hit, that they formally check that properly. So this is a sort of an enabling technology. And beyond MATLAB, MathWorks also has other programming languages. We have Simulink, which is a multi-domain graphical modeling language that has a notion of time built in. And we have Stateflow, which is a finite state machine modeling language. And in both of those, in Simulink and in Stateflow, you can use MATLAB. And that's all powered by this technology, and everything goes to that same IR, so we can target all these different backends. So this really is a fundamental technology for MathWorks that lets us convert MATLAB into the statically typed IR. And so we started the talk by saying, can we do this? And yes, you can. You can go get MATLAB Coder today, and you can deploy high-level language to embedded systems. So that's it for our talk. Thank you very much.
Thank you for the talk. Any question? Yep.
How do you report errors or problems to the user in a way that the developers are able to take action to make it work through the tool?
So I don't know that we do. I mean, I think we, like all compilers, struggle with that. Giving good error messages is hard. So I showed you that report. The report, is where we... It lists out the errors, and it shows you what the compiler knew at the time when the report was generated. So you can use that to sort of crawl through the code and find things that look wrong to you. Like if you know what the code is doing, you say, that shouldn't be a 1x6 matrix. Why is that? And then you can sort of track that. The report has a lot of features that let you walk the call graph. It'll show you specializations of user code, so you can see how many specializations you got and sort of walk that way. But the error messages are a big struggle for our customers. So I don't think we've solved it. We're just doing the best we can. If you have ideas, we'd love to hear them.
You had this whole list of static analysis that you need to do. How do you figure out the order in which they should run to get the most out of them?
So the way internally, I think they're mostly historical accidents, but I think there are good reasons for them. So we run the type inference and the specialization first. That gives us our static IR. And at that point, we have the whole program in our hands, right? We don't have any unresolved function calls. We know what's happening. And at that point, we're pretty close to our standard IR that all of our optimizations analyses are built on. So then we analyze, then we run after that. So like the range analysis, which figures out upper bounds, runs after we've got the inference. The depth before use we run early, like after we've gotten the IR, but we want to run that early because it can uncover fundamental problems in the code, right? If you're reading, I mean, the reason that we do that is that if we didn't do that, we would have to pollute all of our results with it might be empty, right? Anywhere we can't tell. So by doing depth before use, we can exclude the empty case and say, forget about it. Like that can't happen. So we need to run that relatively early because otherwise we're giving wrong information to the user. Yeah.
And the user might step in and say, oh, if you tell me that there's a use without the depth, maybe I should fix it, or maybe I don't.
Can you have an annotation say, I know that it looks like an initialized memory display.
There's a whole bunch of complexity with objects and destructors. Like destructors get injected late in the process and can cause us to go back to an earlier stage and rerun. But it's sort of a lot of details.
So you said that the tool takes even the type inference takes a long time. But what is a long time? It's like, should we be inspired to help you make it go faster? Or what is long?
I mean, for a small example, it's a few seconds. It's not a big deal. But for a large example, we've had customers, for example, there are a range of things. But like I'd say, a pretty normal customer is that it takes 6 minutes to generate code. And it's annoying if that's in your loop where you make some changes and then you press a button and you wait 6 minutes. We do have, examples where the specialization goes wild, and then we've had like essentially bug reports where someone says it took me, it never ended. It just sat there forever. But that's rare. I think that's when people are really pushing the envelope, especially with objects and doing some crazy things.
But I think the alternative is worse. At least I can safely use data that it's not even engineering where I am. Just think of MATLAB C++. That's normally called a graduate student in half a year. And if it's advanced MATLAB, then it's a postdoc in a year. So 6 minutes isn't even terrible to me.
No, I think it's not. It's typically not that slow unless you've done something really bad that trips up the specializer.
So you said MATLAB is really dynamic, but it does not look that dynamic to me compared to JavaScript. So there are some features that you ignore, right? Like, generating code at runtime or things like that you mentioned before. So how much of that code in the usual code, how much part you are ignoring?
So not very much. I think MATLAB allows, like you can do stack introspection in MATLAB, right? Walk up the stack and ask questions about your caller. Like we don't support that for code generation. Like, could we? Maybe. I wouldn't say it's impossible, but normal users don't do that. This is evil programming that we're not big fans of. Now, of course, if some big customer comes to us with a really compelling use case, we'd look into it. But right now, there are other features like exceptions are not heavily used in MATLAB. Exceptions are typically just for errors. So we haven't invested in supporting exceptions, but we have seen some requests, and that's something we'll work on. So there's nothing fundamental that we can support exceptions. It's just we haven't gotten to it. We don't support a val, for example. We'll just take a string and run it.
Yeah, just like in JavaScript. Yeah. Yes.
Have you ever evaluated the performance of your generated code relative to the code that someone might write in the MATLAB to see manual translations that you described?
Yeah, performance is a perennial issue for us. So there are many things that we didn't talk about in this presentation. So I would say that basically the tool is roughly how we describe. We optimize the code, but it's kind of a direct translation of what you wrote, right? So if you didn't write some fancy block-tiled loop, then you're not going to get a fancy block-tiled loop. Like we're not figuring that out from your MATLAB code. So the code, what you get out is kind of what you put in. So the one challenge we have is that MATLAB is a pass-by value for matrices, and so one of the things we've struggled over the years, I think we're getting much better at, is not having matrix copies show up because of MATLAB's by value semantics where they're not needed. So that is one sort of systemic problem, but we think it's kind of under control right now. The other fundamental thing is like if you do matrix multiply, nobody writes matrix multiply as like 3 nested loops that do that, right? There's BLAS or LAPACK have some fancy optimized version. So we do have ways to bring those in. So like if you have LAPACK and BLAS available, there are options. You can make us generate a call to those instead of producing the code for matrix multiply. But for some small target, we will produce sort of the naive loop. That's something we're looking at improving right now. Same thing with FFT. We'll bring in FFTW if you have it. So there are ways of bringing in custom code. You don't have to generate everything from scratch. And that's what we tell our customers when there's a hotspot that's like a specific algorithm. Maybe you have a C library that does that. We have ways that you can bring that into the generated code.
Is your partial evaluator written in MATLAB?
No.
So just to build. So just to build on the question from over here. So if we think of the graduate student who is going to take MATLAB to C++, do you have any user experience where people like to build on the C code that you generate? And then maybe say, oh, I'm just going to, it's great that it's working as a baseline, and then I'm going to just focus on these two cases over here and do the smart thing you said before.
Right. I mean, so we've seen everything. So we've seen some customers use it strictly as a reference. So it's very useful for testing. Like I can generate code, and now I have a reference that I know is right. You know, if you trust MathWorks built the compiler correctly, and then I can write my C code by hand and I can compare them. So that's very useful. We have some customers doing that. We encourage people to say, well, if you really have performance, just write that one small piece in C and then call it from the, like you can bring it in. I honestly haven't seen that many people do it, but I feel like that's like a super useful workflow and that we advertise. I mean, so, yeah, I don't know what else, you know, I mean, we have a targets team that adds support for specific targets, and those they'll, for example, like enable SIMD for a target, or like we use OpenMP for parallelism just because it's portable, but that's actually been a little bit disappointing because Apple decided to drop it, and then Microsoft isn't really keeping up with OpenMP, but yeah, but it's generally worked pretty well outside of those caveats.
I guess as a sort of follow-on to that, is there any interest in optimizing the output for readability of the code?
Yes, yes. So we have had customers pay subcontractors to take the generated code and verify that it matches some spec by hand. They do care very much about readability. I would say, and so we do spend time trying to make the code readable. That is one of our goals. But it's a hard problem. It's hard to quantify, like what you mean by readability. And it's not something I think we're very successful at, but it's reasonable. It's not crazy to read the generated code.
Can you use the information in one run to type check the next run so that it doesn't take as long next time?
Yeah, we've talked about that. We don't do that today. But yes, that is a possibility that we could sort of cache specializations from one and use it in the next.